Hi, this is Kan-Lin speaking. I'm from the National United University Department of Energy Engineering. In the previous section, we've been talking about how to calculate the fuel and the air flow rate depends on the fuel cell operation current, output current, and the stoichiometric ratio, and then the operating mode. Now we are talking about the composition of fuel. In the previous section, we are using the pure hydrogen, but now in this section we assume it's not pure hydrogen. It's a natural gas input goes through the reformer and generate hydrogen-rich gas. Then can we calculate the composition of each stream? It's a little bit more complicated situation. Over here we use you can read we use as a sodium oxide fuel cell or phosphoric acid fuel cell as the example. This example I pick up from the fuel cell handbook. It was added by EG&G Technical Service. You can download this from the website. As you type in Google the keyword fuel cell handbook, you'll find out. The latest version is 7th. Even it's a little bit old, but all the principle of the fuel cell give a very clear description. And I highly recommend to download this handbook. Inside, this is one example inside the handbook. Instead of read the question, the example, I use a graphic to explain what this asking for. That's a natural gas coming in at 500 kilogram per hour. It goes through the reformer. It will generate hydrogen-rich gas such as hydrogen and carbon monoxide, carbon dioxide, and some remain natural gas. The total mass still 500 kilogram per hour. And this hydrogen-rich gas will feed into the fuel cell. The utilization rate is 86%. That means only 86% of hydrogen will be reacted. And then the oxygen, the air, will be supplied through separate stream. And then the utilization rate of the air is 70%. That means oxygen inside the air, only 70% will be consumed. The remainder will be exhausted. In the fuel cell, the hydrogen will be reacted with the oxygen and generate water, and the effluent in this example will be the spent will be going out on the anode side. On the cathode side, there will be the air out. Over here, the hydrogen on the anode side, the hydrogen will be oxidized as a hydrogen ion and then release 2 electrons. And then the oxygen will be react with hydrogen ion and then generate the water. This is for the PAFC. For the sodium oxide fuel cell, the oxygen will be ionized, become an anion, and then go to the hydrogen side, anode side, and will be generate the water from the anode side. That's different. But one important thing is because there's a membrane separate the anode and the cathode, so in the anode side, carbon monoxide, carbon dioxide, water, and methanol will not cross over to the anode cathode side. So the cathode side only the nitrogen and the oxygen and maybe the water will be expelled out. Now the question is there's several questions, and this one coming again. I'll mention this example I pick up from the fuel cell handbook. Is a very good example. And then what they looking for is they give it the condition is I already know the natural gas composition such as carbon monoxide, carbon dioxide, the molar ratio, and then the air. We know the air, and then it's humidify the air, so the water composition molar ratio also known inside the air. And what is want to calculate is the air out and then the fuel out, what the composition of the fuel. The first they want to know is how much hydrogen will be consumed in kilogram, and the second will be how much oxygen is consumed in kilogram mole per hour, and then what the required airflow rate, and then how much water will be generated, and then last will be composition. Now we're going to calculate each one by one. The first we want to know how much natural gas required. So we all the example already give us the molar composition of the input natural gas. Inside the natural gas, actually the natural gas already goes through the reformer. Over here, we already know most of methanol will be converted, methane will be converted into the hydrogen, 75%, and then remain only 4% methane not converted. And the carbon monoxide, carbon dioxide, they had their own molar ratio, and then there's a 3% of water. So total is 100%, and then the average molecule weight more per kilogram more is every more is a 10 to 10.55 kilogram. This average molecular weight of the input hydrogen-rich gas, and the air there's about 1% water in there, and the average molecular weight is 28.74. So we had these two pieces of information. The first we can calculate the mass ratio. That means we know the molar ratio. We can convert into the mass ratio. The first, the fuel over here. The fuel from here we know the fuel molar ratio, and then taken from the input, and then the water. But the water we instead of taking the dry without the water, we can take it as a wet molar ratio over here. We put on the table here. Then we're going to calculate the fuel weight percent and air weight percent. So we put that over here, the table here, and then this is average molecule, the molecular weight for each species, such as methane, carbon monoxide, carbon dioxide, and so forth. And then this is already know the molar ratio in the fuel. Now we can, and then we want to calculate the weight and mass ratio in the fuel. I only give one or two examples. For the methane, is a 0.64. Is a molecular weight times its a molar ratio. Because we over here we assume 1 kilogram, 1 kilomole of the input fuel. Then the methane only account 4%. So 4% times the molecular weight of methane give us 0.64 weight kilogram of methane. So this is how they calculate. 100% more fuel, the methane only occupied 4%. So, and each more only 16 grams of methane. So multiply, you can come out every mole of fuel, methane only 0.64 grams kilogram or something. And for the carbon dioxide is 7.744, and this also the same is 17.6 molar percent, and the carbon dioxide molecular weight is 44 grams. So you multiply these two numbers, you end at 7.744 this number. So you can calculate the rest mass in the fuel can calculate, and the total you can add all this up. It will give you the total weight 10.54. The total weight. That's the average molecular weight of the fuel. Then the same for the air side. The fuel percentage, you can calculate it based on that. Just calculate the total molecular weight is 10.54 gram. For the methane is 0.64. So you can calculate the methane weight percent. The same thing, you can calculate the carbon dioxide. The same. Now we know the fuel weight percentage, the air weight percentage, based on the same principle, you also can calculate. Now we're going to calculate the amount of fuel flow rate in kilomole per hour. And this solution I simply pick up from the fuel cell handbook. And then this is a table we calculate previously. So over here for the fuel supply, we had a 500 kilogram fuel per hour fitted in, and the average molecular weight for kilomole is about 10.54 kilogram. So we can, with the fuel composition, the weight percent also calculate. So over here, the fuel supply, we can, by the 500 kilogram fuel divide by 10.54, we can obtain the fuel kilogram more per hour is 47.44. And next, we're going to calculate the hydrogen supply. The hydrogen composition is over here, the 75%. So each molar of fuel, we had 0.75 kilomole of hydrogen. So we had this 47.44 kilograms more fuel supply per hour times this hydrogen percentage. And then also we're going to calculate the utilization rate is only 0.84. So from here we end up with 30.6 kilogram more of hydrogen was consumed. But if you do not multiply 0.86, then they will end up with the hydrogen flow rate from the fuel. But you multiply the 0.86, you end up with the hydrogen consumption rate. So the fuel flow rate is 47.44 kilomole per hour, and the hydrogen was consumed at this condition is 30.6 kilogram more hydrogen per hour. So this is the hydrogen consumption rate we already calculate. Now next, we're going to calculate the oxygen consumption rate. We put the oxygen consumption rate can be expressed by this flow diagram, and then each mole of hydrogen consumed required 0.5 or one half of the oxygen consumed. So we already know the hydrogen consumption rate, so we just multiply by 1/2 or 0.5, we end with a oxygen consumption rate. That's about 15.3 kilogram more per hour of oxygen. So far we know the hydrogen consumption rate and oxygen consumption rate. And then next, we're going to calculate the required air on the wet air base. With this one, 70% utilization rate. So from this flow diagram, the 70%, we know the hydrogen oxygen consumption rate, but the air is only 70% the oxygen was consumed. So we need to trace back to the oxygen, the air, how much the flow rate required. The composition of the oxygen inside the wet air is given by this table. So from here, we can calculate the air required in molar ratio or in mass ratio. The first, in the molar ratio, that we already know the oxygen consumption rate is 15.3 kilogram more per hour. And then the utilization rate is 0.70%. So we divide by 0.7. We end with how much the actually oxygen will feed in through the inlet, fuel cell inlet. And then this and the kilogram more of oxygen, we want to know the air, the wet air, how much kilogram more the wet air. So the air inside is occupy 20.79 kilogram more percentage of the oxygen inside the air flow stream. So we divide by 0.2079, then we're able to calculate. So this is a total molar flow ratio of the wet air input. Then the mass flow ratio, we simply just multiply by the average molecular weight. From here, on the following table on the right corner, right lower corner, there's a total molecular weight of the wet air. So 1 kilogram more of wet air, the weight is 28.74 kilogram wet air. So we multiply by that, we can coming out with 3,021 kilogram wet air per hour need to feed into the fuel cell. The next is we want to calculate the water generation rate in kilogram more per hour. Since we know the equation, chemical reaction or electrochemical reaction, overall fuel cell reaction, the 1 mole of hydrogen consumed will be generated 1 mole of water. So based on that, we simply just the water generation rate equal to hydrogen consumption rate is 30.61 kilogram more per hour. Now the last thing we want to calculate is the effluent composition, or we already know then the effluent mass flow rate. So over here in this table, the only reactant is the hydrogen.
The hydrogen consumption rate is 30.61. We will calculate. So the remainder hydrogen in the outlet, fuel cell outlet, is 4.9698 molar per hour, given this. And for the other methanol, carbon monoxide, carbon dioxide, and water, they simply just the inner products, just flow through the fuel cell. Whatever coming in will be going out. So on the outside, the fuel cell outlet over here, that's a molar flow rate for those inner species. So the total molar flow rate is you add all this number, give is 16.85 mole per hour. So we know the each molar flow rate and the total molar flow rate. We can calculate the composition molar percentage for this on the fuel side composition molar ratio. We're able to calculate, and the molar flow rate also is 16.85 here. So from here, the inner composition goes feed into the fuel cell, and it's no reactant, so it just simply goes through that and then going to the outlet, fuel cell outlet here. And the only reactant is the hydrogen. The hydrogen will be flow through the fuel cell and then generate, consume and then only remain the 4.98 molar per hour going there. So actually the total mass flow rate or even the molar flow rate on the anode side or the fuel side will be reduced. Some hydrogen will be oxidized as a proton, and it goes through the separator to the cathode side, the air side. So air side, the weight or molar ratio will be increased. So this is inner air side product, but the water actually do not actually be generated inside the fuel cell. So water even is not reacted, but since it generates from the oxygen reduction reaction, so actually its number will be increased, flow through the fuel cell. So the nitrogen is in the product, so the number will remain the same. But the water, since it will be generated, because hydrogen will be migrated through the separator and then react with the oxygen and then generate water. So water molar ratio flow rate will be increased from 1.05 to 31.66 mole per hour. And then since you can see that's what happened. And then the oxygen will be oxidized, reduced, be consumed. So the number of oxygen in the effluent will be reduced. So the total molar flow rate will be given as 120.5 so far total. So the next one, we're going to calculate the composition of the spent oxide on the air side. The same thing, on the air side, the nitrogen inert, there's nothing react, so whatever coming in or going out. And then the water will be generated due to the fuel cell reaction, so the molar flow rate will be increased from in the outlet side. And the oxygen will be consumed, so the number will be reduced. And then total molar flow rate, you add all this number up, is 120.5 molar per hour. So based on that, we can calculate the molar percentage composition in the air side. So given by this. So in summary, this is the schematic present of this question. And then this is presented by this question. And then for the A, the hydrogen will be consumed. The flow rate is how much hydrogen will be consumed is 30.6 kilogram mole per hour. Hydrogen will be consumed, and the oxygen will be half of that because the reaction shown by the red equation. So only half of the oxygen will be consumed. And how much air should be coming in? Consider a 70% utilization rate. So in the molar flow rate and the mass flow rate can be calculated. And then how much water will be generated. The 1 mole of hydrogen will be consumed will be generated 1 mole of water. So the hydrogen consumption rate equal to water generation rate. And then how much water composition of effluent over here. So the effluent out we're able to calculate, and then on the fuel side and the air side we're able to calculate.